Welcome to this explainer. Right away, we're diving into the exact data pipeline you need to turn a standard, off-the-shelf drone from a fun little private FPV toy into a seriously powerful shared asset for real-time situational awareness. We're going to focus strictly on MAVLink to ATAK integration and how we achieve real-time drone telemetry via CoT. Let's just jump right in.
So, the core concept we need to get out of the way immediately is the profound difference between a video feed and full telemetry. You see, video only tells you what the drone sees in that exact fraction of a second. It's basically a keyhole view of the world. Telemetry tells you exactly where the aircraft is in space, its attitude, pitch, roll, and yaw, and critical health stats like battery life. Relying on just a video feed is super limiting, but combining both, that's what actually creates true situational awareness.
Without that telemetry on a shared map, an isolated pilot is essentially forcing the rest of the team to operate completely blind. Think about a search and rescue team trying to figure out exactly which tree line or dirt road a pilot is looking at over a crackly, scratchy radio. It's wildly inefficient, and honestly, it can be downright dangerous. We need everyone on the network, not just the guy with the controller, to see that aircraft as a live, moving track. To solve this massive operational headache, we use ATAK. The Android Team Awareness Kit is this incredibly powerful geospatial app. Think of it as a highly dynamic, shared tactical map. It lets every single operator on a network see live tracks of critical assets. People on the ground, vehicles, sensors, and yes, drones. ATAK puts all of it into one unified, real-time picture. And hey, there are sister apps too, like WinTAK for Windows and iTAK for iOS, and they all speak this exact same language. Speaking of that language, ATAK relies on a very specialized messaging standard called Cursor on Target, or CoT. Originally built by the U.S. Air Force Research Lab, CoT is the XML-based standard that this entire TAK ecosystem runs on. In this system, every single thing on the map, whether it's a person, a danger zone, or our drone, is represented as an XML document, which they call an event. Make no mistake here, if you want anything to show up on an ATAK map, you absolutely must describe it using Cursor on Target. It is the absolute gatekeeper. Let's actually look at the anatomy of one of these XML events. A CoT event needs a few specific data points to render properly. You've got your version, a unique ID, and a type code, which is what dictates the exact icon that pops up on the screen, like a friendly helicopter, for instance. But I want you to pay close attention to the bottom of this list, the stale timestamp. This is absolutely crucial. For a drone that's updating every second, you'd probably set the stale window to maybe 5 or 10 seconds. If the data link suddenly drops, this timestamp ensures the drone icon just vanishes. That way, you're preventing some misleading ghost icon from permanently freezing on your map and confusing everyone. Now, amazingly, getting a marker to actually appear on the map is incredibly simple at the network level. Just one single UDP packet containing a CoT XML event sent to this default multicast address and port. That's 239.2.3.1 on port 6969, will make a marker instantly pop up on any ATAK device on your local network. It is literally the ultimate hello world for this whole ecosystem. In a world completely bogged down by complex military tech bureaucracy, it's pretty refreshing that one simple UDP packet is all it takes to put a dot on the map. Okay, let's switch gears for a second and look at the drone side of the equation. Drones don't naturally speak CoT, right? They speak MAVLink. MAVLink is this highly efficient, really lightweight messaging protocol used by popular flight controllers like ArduPilot and PX4. It's exactly how the drone talks to its ground control station. And just a quick tip, if you're setting this up yourself, version 2 is highly recommended. It gives you 24-bit message IDs and way better bandwidth efficiency compared to version 1. So what exactly is the drone shouting into the void? Well, there are 5 vital MAVLink messages streaming from that flight controller that we absolutely need to capture. The heartbeat message just proves the drone is actually alive. Global position int hands over the 3D GPS coordinates. Attitude gives us the tilt and rotation. Battery status, as you'd guess, keeps us updated on power levels. And mount orientation tells us exactly where the camera gimbal is currently looking. We have to grab these specific messages and translate them for our tactical HUD. Right, let's look at the pipeline that bridges the gap from the drone's flight controller all the way over to the operator's ATAK screen. It all goes down in 4 really distinct, rapid steps. First off, the drone streams its MAVLink data. Second, a gateway translates that raw data into Cursor on Target. Third, the network transports it. And finally, step 4, ATAK renders it on the map. Let's dig right into step 2, because honestly, that's where the real magic happens. Because the drone and ATAK speak totally different languages, we need a translation gateway. basically a bridge process. This bridge is heavily dominated by the Python ecosystem. It simply subscribes to the MAVLink wire, reads those incoming messages, and spits out CoT XML. Tools like PyTAK and pymavlink are the absolute standard libraries here. You can totally build your own, or you can just use existing setups like SICWove or the official ATAK UAS Tool plugin.
Inside that gateway, those raw MAVLink fields are directly mapped over to CoT XML elements. It's actually a pretty elegant translation. Global position _int maps straight to a latitude, longitude, and altitude point. The drone's yaw, pulled from the attitude message, becomes the heading vector, which shows us exactly which way the nose is pointing. Battery status becomes its own custom detail element. And crucially, mount orientation is transformed into a linked polygon. This projects the camera's exact footprint directly onto the ground map.
Once the translation is done, we hit step 3, transport. You basically have 2 paths here. You can dump the telemetry onto a local multicast. This takes 0 infrastructure and is absolutely perfect if everyone is sitting in the same room on the same local network. But if you need to share this situational awareness with a globally distributed team, you'll want to route it via TCP or TLS through a ATAK server. That server then fans the data out to every single connected client, no matter what network they happen to be on. And that brings us to step 4, the ultimate payoff on the ATAK screen. Thanks to our translation gateway, the drone doesn't just show up on the UI as some boring static dot. It's a living track, updating every single second. You get a clear heading line showing the aircraft's direction. And even better, you see this glowing polygon on the map, the sensor footprint cone, showing exactly where that camera is looking on the ground, right next to live battery readouts. I mean, it is total, uncompromising situational awareness. But hey, we certainly aren't abandoning the video feed. We're actually bringing it directly into the map. By routing the drone's RTSP video stream through a server like MediaMTX, our gateway can broadcast a special CoT video alias event, specifically using the type code B-IX-I. In practice, this is incredibly convenient. An operator can simply tap the drone's moving map icon, hit View Video, and boom, the live feed opens automatically. No one has to frantically type out clunky stream URLs in the middle of a high-stress operation. Now, brace yourself for a pretty staggering contrast in bandwidth. If you're on a constrained tactical radio, say a 5 megabit per second man-at radio, bandwidth is your precious lifeblood. A standard H.264 video stream is going to hog around 250,000 bytes per second, but a full telemetry stream, that takes at most 2,000 bytes per second. Telemetry is so remarkably lightweight that you should absolutely always drop your video resolution before you even think about throttling your critical map data. But what if you find yourself in a highly constrained RF environment where literally every single byte counts? Well, you can actually optimize the telemetry even further. Newer ATAK servers and ATAK builds support a binary, proto-FUF encoded version of cursor on target. If you switch your gateway from standard XML to this binary format, you can shrink your telemetry payload size by an unbelievable 55 to 65% on the wire. It's a massive optimization. Now, as you start scaling up from a single drone to multi-drone operations, strict discipline becomes key. You have to enforce stable, unique UIDs and strict call sign schemas, like UAS Alpha, for example, so your operators know exactly which video feed belongs to which icon. You'll also want to throttle your gimbal updates down to maybe 2 to 5 Hz just to save radio bandwidth. And this is a big one. If your drone natively outputs CoT out of the box, you must disable any redundant gateway broadcasts. If you don't, your map is going to devolve into a chaotic, unreadable mess of overlapping ghost targets, which entirely defeats the purpose of situational awareness. So we've clearly mastered pushing data from the drone down to the map, but that leaves us with an incredible final thought to ponder. What happens when the map controls the drone? The ultimate, most complex evolution of this entire pipeline is bidirectional control. Just imagine drawing a route or a point of interest directly in ATAK, having the gateway translate that backward into MAVLink mission items, and watching the drone instantly fly to that exact location. ATAK essentially becomes your full mission planner. It's a wild concept, but that evolution is definitely a deep dive for another explainer. Thanks so much for joining me as we unpacked MAVLink to ATAK telemetry integration. Keep learning, and I'll see you next time.